So, are you listening to me? Okay. So, this is our last activity, our event. And with great pleasure, now I'm going to introduce Professor Gastao Krein. And he's a professor of the house, as you can see. He's a full professor at the house. Gastao Krein is one of the greatest specialists in QCD, hadronic physics, and the like. He's been working with important people in the field, such as Craig Roberts, Anna Hasenfratz. It's Anna, right? It's Anna Hasenfratz at your work.
Hmm?
You work with Anna Hasenfratz, not the...
No.
No? We didn't?
Not even Peter.
No, okay. So, yeah, he's joking, but...
You
anyway,
forgot
so
to
he's
mention
going...
yourself.
Okay. He's going to put some of his experience in all this hadronic physics to present us a little bit about this work of complex masses and the bound states, and we are eager to hear about it. So please, Gastao.
Thank you.
You have 2 minutes to talk.
Thank you, Gabriel. And thank you also, I don't know who did it, but if you look at the page of this event, I start at 3 and there is no time to stop, right? So, all right. First time, I will have infinite time. So why I'm talking in a quantum gravity event? As he mentioned, I'm a QCD guy, okay? Hadronic physics. We have a new fellow, ICTP, Simon's fellow. He's Italian, he's learning Portuguese. Once he came to my office and asked, what do you mean by picareta? When you when you call someone picareta, okay? I had some troubles to explain him. I said, it's something common in the physics departments that we call each other. But I think this also applies here. Okay, I'm working in quantum gravity as a picareta. Okay, I don't know if you understand it in Spanish, but no, picareta. Okay, later we'll explain. Okay. Actually, this has to do with a paper. It's one of my most cited papers that was just, we sent it out when I was moving to São Paulo, and we completed this paper with Craig Roberts and Tony Williams. And this is the old times. Is the date there? Good, it's not. It's a very long time ago, okay? And all this stuff of Dyson-Schwinger equations and dynamical chiral symmetry breaking in QCD was starting at that time. And we wrote this paper connected to confinement, and we examined some detail on possible scenario for confinement where colored propagators have no mass poles on the real axis. So, so this talk has to do with that, and since then I have been working on this kind of things, okay? So what is the connection to quantum gravity? I hope by the end it will... So here I will use one thing that Villa-Lobos used to say. Villa-Lobos, Brazilians know who he is. Okay, he's a famous composer, was a famous composer, and was always invited to small cities for concerts and things like that. But people there were not interested in this very fancy music, only some samba or something like that. But he told, fine, you go there, play what they want, but also play some good thing for them. So this, I want to imply that QCD is such a good thing. It's the only quantum field theory that we know that is finite in the infrared, in the ultraviolet, well-defined, and QED is one of the worst quantum field theories we know, but QCD not, is a perfect quantum field theory, okay? And everybody, I think, knows what is QCD, is defined through those to that Lagrangian, and the basic degrees of freedom are quarks and gluons, and they are not the degrees of freedom that are observed in detectors. Nevertheless, they make up the stuff that we observe, okay? And we believe that it is the right theory of this strong interaction. Why? Because it has reproduced the hadronic spectrum from that Lagrangian, okay? Since the Lagrangian has parameters, which is the coupling constant and quark masses, you need some input, okay? So these are in red, these in blue are inputs, and the rest is, say, computed with those parameters, okay? And since it came out in Science, it got to be right, okay? Another paper in Science regarding now the difference between the hadron masses, okay? Just from first principles, including electromagnetic interactions, okay? Again in Science. Even Nature, QCD made it. This has to do with a very important hadronic quantity that is the weak axial charge, okay? And why are we still studying QCD if we know it's correct? We should do something different that we don't know, okay? Well, that are numbers that came out from a computer, okay? You put the Lagrangian and then the numbers came out, but we don't understand how that happened, okay? What actually are the mechanisms that lead to those masses? And this is a nice book by Wilczek. He put it very, very well, this question, okay? That we don't understand how QCD works, okay? Quark and gluon confinement. What is the meaning of quark-gluon confinement? Different people mean different things for confinement, okay? I think what is safe to say that it is an experimental fact. Quarks and gluons are not observed in detectors. So this is one definition of confinement. So as I said, means one thing for some and another for others. Pure Young-Mills and quench QCD are not QCD. Some people confuse Young-Mills, features of the Young-Mills theory with QCD. The thing is that QCD has light quarks, okay? Pions, for example, which leads to pions. They exist. So one cannot switch them off in one's mind, okay? You can do it or you can switch it off in our mind or in our computer, but not in nature. They are always there. So Young-Mills, pure Young-Mills, is not an approximation to QCD. It's a different theory, okay? Of course, it contributes. It's an important part of QCD, okay? But it's not QCD by itself, okay? If you ignore light quarks, you are not talking about QCD. Since the early days, many claimed proofs of confinement. Okay, I have been in conferences where guys are giving talks and say this proves confinement. Okay. Some use lower dimensional field theories. Okay. It's nice to work. It's a nice mathematical physics exercise, and sometimes you get insight in lower dimensional field theories, but it's not QCD in 4 dimensions. Others have in mind springs, strings, flux tubes, okay? Wilson loops, linear rising potential, dual QCD, vacuum topology, solitons, all these things are brought in to explain confinement. But it is still an unsolved problem. But as I already shown, lattice QCD has brought some light on that. This is something that many have in mind about confinement, okay? That say you have a pair of quark and antiquark forming a meson, okay? So when you try to separate the quark from the antiquark, you have a kind of a tube of force here, okay, that extends, and if there is enough energy here to create a light quark pair, then you gain two mesons there. So this string that forms there, it might happen, okay, and the essence of the problem is that you have the light quarks in the theory, so this will happen, this will break. If you see a picture of someone drawing a QCD flux tube of 10 centimeters, this is wrong, absolutely wrong. It has nothing to do with QCD because it breaks, okay? So this is a lattice simulation of just of that feature. You have say a source of color fields in one point, another source of a color field, color charge you can here, and they're separate, and you see clear an energy density there that forms between these two charges, okay? So if you start separating, okay, this is still there, okay? Here are the distances, okay, for this particular simulation, okay? But eventually this will break. You see here, this breaks the separation between these color sources, they separate. So there, what happened here, okay, a light quark went to that source, another light antiquark came to that source, and then what is in the middle here is nothing, okay? So this is the realization of that picture that I have shown. So this is a fact. But there's another lesson here, okay, that some people don't want to hear it, is that the distance that this breaks, okay, if you make the accounting of the energy stored, the value of that string tension and all that, you discover that the breaking is at distance RC, which is of the order of 1.2 Fermis, and for non-static sources, and if you use actually the physical pion mass, you can estimate that the string breaks at less than 1 Fermi, 1/3 of the Fermi. So what is the meaning of that? You know what is the size of the proton? The proton is of the order, the radius of 0.8 Fermis. This is 0.3 Fermis. So the string never gets out of the proton. There is not such a thing of a string between two hadrons. This never happens, okay? This is simply not what happens in nature, okay? There's not such a thing like strings, okay, extending between hadrons, okay? So there's no flux tube in QCD, okay? If someone comes to tell you, I'm doing simulations of QCD flux tubes and Reggie trajectories, huge flux, it's all wrong. It has nothing to do with QCD, okay? This is one lesson, okay? This comes out from QCD, from lattice simulations. How do people understand this, okay? So there are many ideas. I will show one of such ideas, which is positivity violation in propagators, okay? If you have a physical particle, so this is a propagator, okay? just for the example, I'm using here a scalar field just to illustrate the point. Okay, so then you have the Fourier space, and this has a spectral representation, which is the Chalain-Lehmann representation that we have seen many times during the week. People talking about that. Okay, so this spectral representation is based on basic principles of physics: unitarity, causality, positivity of the norm, and all that. Okay, so based on this rho of p square must be positive. So this will be a physical particle. Okay, so if you have a particle propagating, okay, it can reach the detectors. Okay. There is also a theorem in quantum field theory, which is not that well known, but I think everybody knows this theorem, is the following. The positivity of the spectral function implies that propagators have no zeros or poles of the real axis. I'm talking about the first Riemann sheet of this thing. Okay, it can have a pole and then a branch cut. Okay, there is nothing here in the complex plane here. There are no poles or zeros here. If that spectral function exists, that spectral representation exists, and it is positive, you can prove it in 2 lines. Okay. So this is all for, say, what is called a healthy field theory, okay, in which the fields that represent the particles are physical particles that can reach the detectors, okay. So, as I said, a lot we have learned from lattice, and lattice calculate propagators. Propagators are not physical objects, okay? They are gauge dependent and all that. But some features of the propagators are physical. For example, if the propagator has a pole, that pole is gauge invariant in general. Okay, so there is a physical information in non-physical objects. Okay. And lattice can compute that in Euclidean space, of course. Okay? And then in Euclidean space, that spectral representation of this. So we don't have propagate time ordering thing. What we have there, we have Schwinger functions. Okay? So the Schwinger function has a spectral representation. This is the same rho that appears in the propagator. Okay? And then you see here, okay, rho is supposed to be positive. This is p squared. Euclidean is positive, and this is integral from 0 to infinity. All this is positive here. If you take the derivative with respect to p squared, okay, if you differentiate that, you get this minus sign here. So the derivative of the propagator, suppose lattice computes that, okay, it should give a negative, should always be negative as a function of p squared, the derivative. Okay, it should look like this, okay, for a healthy particle, say. That is the behavior of the propagator, and then you see the derivative is always negative, okay? On the other side, if you have, suppose lattice comes out with a propagator looking like that, what happens? Here, the derivative with respect to p squared here, okay, is positive, is not negative. So it violates that condition. And where that violation comes from the fact that rho then is not positive. Because p squared plus sigma squared is obviously positive. And the only source of negative contributions is coming from rho. So then rho is negative, and that violates positivity, and that is what we call positivity violation. Okay? So let's see what comes out with. This is the first lattice calculation of a propagator. Okay? This was for the gluon propagator in SU2 SU2 Young-Mills theory. Okay, was done here in São Paulo, in USP of São Carlos, in São Carlos. Okay, by Atílio, Teresa, and André Taurines. That was a student at that time, and see what comes out. Okay, you see clearly here this thing, a signal of positivity violation in the gluon propagator. Okay, this is a computation, okay, using the degrees of freedom of pure Young-Mills theory. Okay, so pure Young-Mills theory seems to violate positivity. So this will indicate that the gluon is not physical. Okay. This is very recent, from 2023. They use a different way to plot this. Okay, they consider this quantity here. Okay, they separate here the zeros. They use only one. From these 4 Euclidean momenta, they use one and make a Fourier transform of that. Okay, and then you have C of t. This is positive and this is positive. So this C of t must be positive. And you see what they find here. Don't pay attention yet to this here. Just look here that you have this negative part here. So that quantity, 2023. And this is SU3 with quarks. This is QCD. This is not pure Young-Mills. Okay? So it seems QCD has positivity violation. Okay. So this is all lattice. So can we get an understanding of that in continuum? Okay. So how do we treat propagators in continuum approaches? Okay. This is one way is through these functional methods. Okay. And this comes with the name of the Dyson-Schwinger equations, that are the equations of motion of correlation functions, okay, of propagators. Okay, so here you have the Dyson-Schwinger equation, for example, for the quark propagator. Okay, this is the inverse of the quark propagator, is the non-interacting quark propagator, and here you have the self-energy. So these dots here are the full propagators. These are not perturbative. Okay, these are full propagators. You have the vertex, quark gluon vertex. You have the gluon propagator and the quark propagator. If you give me this vertex function and the gluon propagator, I can solve this integral equation. This is an integral equation. You understand it, right? Because you see this is the full inverse propagator, and here is the full propagator. So the full propagator appears inside the integral. So this is an integral equation that you have to solve. Okay. Now, if I want the quark gluon vertex, it has its own, here, quark gluon has its own Dyson-Schwinger equation. Okay. You see here, this is a 2-point function. We need 3-point functions here. This is the 3-point function that we need here. But to get the 3-point function, I need the 4-point function. To get the 4-point function, I need the 6-point function, 8-point function. So this never closes. Okay. Same for the gluon propagator here. You have the gluon propagator here. These are all the contributions of the gluon propagator, and this is an infinite set of integral equations, okay, that there is no hope to solve it in closed forms. So what people do, okay, some people they borrow from the lattice, say the quark gluon vertex. This has not been calculated yet in full, all the components of the quark gluon, only some parts. But the gluon propagator has been computed. Some people borrow that from lattice and put it inside there and solve that equation self-consistently, okay, and get results, okay. Others simply make ansatz. For example, for this combination, the gluon propagator times this vertex, you guess it. Has to have asymptotic freedom, so At high momentum, this has to run according to perturbative QCD, so you make an ansatz that it matches ultraviolet, and here in the infrared is no man's land. So then it's open to gases and wrongdoings of all sorts, okay? And this is what people have been doing since that my first paper that I have shown there with greater and greater sophistication, okay? And one feature that invariably happens is the following. Whatever you do in general, okay, if you make an ansatz for this quark gluon vertex times the gluon propagator, there are models in the market, okay, there are some famous, others not so famous, okay, and you solve for the quark propagator that the most general form is this one in Euclidean space. Okay, you have this what is called the running mass function, and you have this wave function, the dressed function. Okay, the dressing function of this thing, and you compute these things in your model. Lattice has computed that too. Okay, and so what I see. So you have here the running mass. You see this MeV. In the infrared here, this is the Euclidean momentum. In the infrared is of the order of 400 MeV. So this is the mass, the infrared mass of the quark. 3 times 400 is 1 GeV. This is the proton mass. So we understand where the proton mass comes. It comes from these stressed quarks, these constituent quarks. Is stressed by the gluons and all stuff that is involved in that thing, okay? Because in QCD, these masses that appear in the Lagrangian are 5 MeV, 2.5 MeV. These are the current quark masses, okay? Are those that appear in there. This is already the solution of this thing. So what are the poles of the propagator, okay, is when p squared is equal minus m squared, okay? That will be a pole. And for this particular model here, okay, there is a real pole, is shown here, okay? Here, more or less, at some p squared minus mq squared, there's a number that we can look up here, which is the pole mass, okay? This will be, say, the physical mass of the quark. But it's not only that they find. Okay, they find also complex poles. Okay, so these are different values of the parameters that is a parameter that parameterizes the infrared. Okay, this W here. It doesn't matter much what is it's just a parameter, and here this guy here has changed that values, and you see how they move. For example, if you have omega, you have a pair of complex conjugated poles here. If you change this a little bit, these poles move. So it depends on the strength of the infrared, okay, how strong is the quark-gluon interaction, okay. So the complex poles can be in different places. So the quark propagator has a real pole, but has also complex conjugated poles. And that is perfectly right, okay, because from deep inelastic scattering, we know that the quark can be described as a free particle, and so these are running masses. So when MP squared is large, these masses go small, you see, it goes small here, okay? It goes very small. These are the masses that people use in deep inelastic scattering, for example, okay? But the quark cannot propagate much because then it hits the complex conjugated poles. So then it cannot reach the detectors, okay? It will blow up, okay, and will hadronize, will do something, okay? It will not reach the propagators, the detectors, okay? So this is fine. We have, say, a picture that at high momenta you have essentially free quarks, okay? But in infrared, when the momenta get smaller and smaller, you get these complex conjugated poles, okay? But these objects, they form the hadrons, okay? they are what compose the proton, the pion, and all that, okay? How do we calculate a pion mass, for example, okay? This is through what is called Beatty-Salpeter equation. If you look at Zuber, there is one chapter there that he discusses the bound states of electron-positron, okay? Solving this equation, okay? So this kind of equation is the quantum field theory equivalent, one of the quantum field theory equivalents of the Schrödinger equation for calculating bound states, okay? So what is the input? The input are the quark propagators. So these are the quark propagators with complex masses, okay? And then you have this is what I want, okay? This is this will give me the mass of the particle. When this equation has solution for some p squared equal minus m squared, this is Euclidean. So always the pole is on p squared minus the mass squared. Okay? If this has a solution, so this is the mass of that bound state. This in particular is for the pion. Okay, this is the vertex function here for the pion. You have gamma 5. This gives the quantum numbers of the pion. Okay, there should be also some tau matrices there to give up tau plus, tau 0, or tau minus, but never mind. This is trivial, but the important part is gamma 5 here, and these are the different amplitudes that contribute to the vertex function. So the thing is, this has complex conjugated poles, this has complex conjugated poles, but the thing is that complex things here and here, they essentially, their products, when you compute this thing here, it gives a pure real thing. They just enter in the exact way to give only real contributions. Okay? And what you find, when that mass in the Lagrangian is equal to 0, the solution of this equation for the quantum numbers of the pions gives a 0 massless particle. And what is that? In the chiral limit, we have a Goldstone boson. This is the breaking of chiral symmetry. Because if MQ is equal to 0, and the propagator has that big m there, m of p squared, that breaks chiral symmetry. Okay, because if the propagator has a mass term here, 1 over p slash plus m, for example, if this is different from 0, this breaks chiral symmetry. Okay? So dynamically, you generate mass, it breaks chiral symmetry. So it breaks the symmetry, there should be a Goldstone boson in the spectrum. And there it is. This is the result of a numerical calculation, okay? For that same ansatz that we use for solving the Eisenschwinger equation, we use it here for the Beatty-Salpeter amplitude for the pion. Now, if we are away from the chiral limit, we are in the physical limit, where you use the m quarks equal 2.5 MeV and 5 MeV for the U and D quarks, you get a massive pion. And also, if I compute this for the other mesons, for the rho, for the omega, for D mesons, for all mesons, okay, you put complex conjugated propagators there, and what comes out are massive real poles. Okay, in nothing else. Okay, you don't get junk together with that. You always get, because all these imaginary parts of the class, they combine such the thing is real. Okay, and you get, and all the hadron mass spectrum has been computed in this way, in this model. But this is always a model, okay, because we cannot solve that chain of integral equations in the closed form. You always have to make an ansatz, a truncation, and things like that. The more money you have, the more possibility you have to hire postdocs, and the level of of sophistication of the computation always increases. Okay, what they call improvement. Okay? Anyway, so this is what we do today. Okay, different models, okay, and different things. Okay? But how do we understand this? Also, Lattice came to our rescue. Okay? That what are the important configurations of the gluon? If you imagine, this is the gluons in the vacuum. Okay, these are the gluonic fluctuations. This is a lattice simulation that computes the gluon field fluctuations in the vacuum, or the QCD vacuum. Okay, and what are the important configurations here that led to positivity violation, complex poles, and where this comes from? Okay, and Lattice came with a confirmation of some gases or whatever from very old times, from Toft, Greenside, Faber, Langra, and others, okay? Even people sitting here in the audience, okay, that claim that the important gluonic configurations are what is called the center vortices, are solutions that resemble tornadoes of these gluonic configurations. This was a guess, say, or based on models from the early days of QCD, okay? But Lattice, look here. This is the string tension. Remember that I said that in pure Young mills you have the string tension. If you separate these two color sources, it never breaks. Why? Because you don't have like quarks. This is only pure Young mills. So then you have this linearly rising potential. Okay? So this is with different, if you have, so this is vortices only. So if you have only vortices, they have a way in lattice QCD, they have a way to remove these vortex configurations or remove the rest. Okay? So if you have only vortices, you have a linear rising potential. But at the moment, from the old configurations of your Monte Carlo simulation, you remove the vortices. Remove them. What you get, you don't get a linear rising potential. You have some short distance thing here, Coulomb, something like that, but then it flattens out. Okay? So if you remove the vortices from that ensemble of the path integral that you are going to use to compute this thing, this doesn't give a linear rising potential. Okay? Another thing, this is the quark mass function. Okay, remember this mass function that I showed, the mass function of the quark that I showed, from where we get the pion and all other things. Okay, what you see here, if you have untouched configurations, meaning leave everything is there. You run your machinery, okay, Monte Carlo simulation, and you compute the quark propagator and look at the mass function. What you get this thing here that we get in models and all that. You see here this number, 400 MeV. This is the constituent quark mass. Okay? Now, take from those configurations that you have, remove the vortices. What remains there? Zero. There is no dynamical chiral symmetry breaking. Okay? There is no this mass generation mechanism. Okay? It simply is not there. Okay? So if you don't leave the vortices there, you don't have dynamical chiral symmetry. You don't have mass generation. If you don't have mass generation, you don't explain the proton. You don't explain anything. Okay? Giving all this, okay, so we have this in the continuum, we have a understanding this, perhaps these are complex conjugated poles, positivity violation, and things like that. We have some support from the lattice, okay, but these center vortices are difficult to model. Okay, it's not something simple that you can put in your path integral and compute things. Okay, But we are in this direction. We are doing that. Okay, so I used to say, it's up to you here to connect the dots. Okay. A model understanding, for example, this is a quark propagator computed directly in Minkowski space, also with a model, of course. Always you have to use a model, okay? Use a simple model. You do a gluon propagator with a mass there. You have the gluon propagator, is simply the G mini plus K mu over K square, okay? So this is the gauge thing, and now you have here 1 over K square minus M gluon square, okay? Put this there in the Dyson-Schwingel equation, solve it, positivity violation. You see here, you get positivity, solve it self-consistently, not in perturbation theory, okay? You solve that Dyson-Schwingel equation in this approximation here. You have the gluon, which is this one. Okay, here you use the bare vertex, and here is the full propagator. Solve this self-consistently, and what you get, extract the, once you are in Minkowski space, you have access to the spectral function. It's the imaginary part of the propagator. Okay, then I get the spectral function you see here. The spectral function is negative for some values of the variable that defines the spectral function. Okay, you get positivity violation from an analytical, from a model that has, say, ultraviolet asymptotic freedom, and in the infrared you put a gluon mass here. Okay, fine. Even in perturbation theory, you take the gluon propagator, you compute it in perturbation theory. One loop perturbation theory. Duffy made the calculation. This is her graph, okay? Compute all that, okay, the gluon propagator, all contributions to the gluon propagator, say this one, plus, is the quark loop here or not? No? No quark loops, pure Young-Mills, okay? And the ghost. Okay, you solve this, okay, in perturbation theory, and you look at the inverse of the propagator, you ask, where are the zeros? Complex conjugated poles, okay? It shows complex conjugated poles. Now, just to mud the water a little bit, okay, sujar a água pouco, certo? Actually, this complex conjugated poles is a bit controversial, okay, because you can get all this with plain Yukawa couplings and all that, okay? It might be a feature of the approximations. Okay, this is pure Yukawa couplings, okay? If you use perturbation theory or simply the rainbow approximation, if the coupling is sufficiently strong, you get complex conjugated poles. Has nothing to do with confinement, right? This is Yukawa coupling, is Yukawa theory. Nucleons interacting with the pion. You look at the propagator, it has complex conjugated poles. It must come only from the approximation you did, or you use in perturbation theory where it's not valid. The coupling is too strong to use perturbation theory, okay? So it might be something. If someone comes with complex conjugated poles, it might not be real. Of course, the poles cannot be real. It might not be real effect. It might not be a real result. It might be an artifact of the calculation. But we have lattice. Lattice has shown complex conjugated poles too. Has shown positivity violation, okay? So we are in the middle of this confusion here. So what are the perspectives from today, for example? Okay, all these continuum people that work in the continuum, and they more or less rely on this picture of complex conjugated poles to explain confinement, okay? Others not, to use other things, but I think it's fair to conclude that unless we gather more knowledge about such issues, our understanding of QCD, at least the non-perturbative QCD, is not more than superficial. Okay? How lessons learned in QCD might be useful in quantity. Here the picareta enters. Okay? So how these lessons that we have seen from QCD modeling and even lattice, okay? We always claim that, lattice has seen it, it must be right. They also have their pé de barros, como a gente diz, pé de barro. They also have some dirty there, okay? But there is increasing evidence that this actually is a feature of QCD, okay? What can be useful in quantum gravity, okay? So there are two prominent QCD features that might be useful. One is these complex mass poles in propagators, because I think during this week we have seen many talks saying that perhaps there are some ghosts in something. I don't understand quantum gravity, okay? Don't blame on me, okay? And also another feature is the complex action, Euclidean complex action, okay? So what is this? The first thing I already explained here, okay, is that all this that comes out from lattice and continuum. But what is this thing here? This is the following, okay? So if you are in the vacuum, okay, you have that the partition function is simply the psi A e to the minus S Euclidean of QCD. Okay, and from there is all what lattice cares, uses that, and that's it. Okay, here is the Euclidean action of QCD. Now, if you want to make a finite temperature, it's still the same, but this then is the Euclidean action with one dimension compactified, which is the finite temperature thing. But how about finite density? Okay, I want to simulate neutron stars. What is this stuff inside the neutron star? In the core of a neutron star, what is there? Okay, it should come out from this partition function in the presence of a chemical potential, mu b. This is a baryonic chemical potential. Okay, it enters there, but how it enters in the Euclidean action? It enters with a term like that. So the action, Euclidean action, as a function of mu, okay, this is the part that depends only on mu, okay? You have this one that doesn't depend on mu, plus this one. This is the contribution from the chemical potential. You know that the partition function is trace e to minus beta h minus mu and baryon. You express this partition function, this trace, in terms of a functional integral, you get this in Euclidean space, okay? So what is this contribution? Minus or plus, I don't remember, I mu integral d for x psi bar gamma 0 psi. This is the contribution to that action. The Euclidean action is not real. S of QCD as a function of mu, complex conjugated, is different from S QCD mu. So the QCD action in Euclidean space in presence of a chemical potential is complex. Nevertheless, okay, you can compute things with a complex action in Euclidean space. Perturbation theory, you can do perturbation theory, okay? It might not be useful for neutron stars, but you can compute whatever you want, okay, the pressure, whatever you want in perturbation theory. It might not be applicable, but you can compute with complex actions. It's not a fundamental problem here. is a problem from lattice simulations. Why? Because they use Monte Carlo. Okay? For Monte Carlo, this must be a positive. Okay? Because this is the probability with which they search for the configurations, the important configurations that contribute to the path integral here. Okay? Once this is complex, this is not the positive. It oscillates. This is what is known the sign problem. Okay? Condensed matter has this problem of complex actions. Okay? It's a problem for Monte Carlo simulations, but not in principle. So this feature also will appear in a... Now I will stop here, go to the blackboard to explain one thing that Ilia and Manuel put me in. Okay? I heard they discussing that, and Ilia told me, look, if you can prove that the goals that we have form bound states, like your bound state of QCD, I pay you dinner every time we meet. And you can choose the wine. Okay, so I'm here now to collect the dinner and the wine. Okay, so what is the Elias problem? The Elias problem is the following. This is the part I don't understand well. Okay, I will just make like papagayos. Okay, we'll repeat what Elia told me. Elia told me that he has some model that the action, okay, the Euclidean action is d for x